Welcome to Data Structures and Algorithms, the Egg Edition. Today's topics, trees and graphs. A tree is an abstract data type that is based on linked lists with nodes. A popular tree is a binary search tree, which I explain now. A tree has a root, the first element of a tree, and several nodes. Each node stores a key that is bigger than all the keys in the node's left subtree and smaller than those in its right subtree. Each node can have max 2 next elements. A tree has no unconnected nodes, and in trees, nodes cannot be connected in cycle. Let's build a tree with surprise eggs. First, the root surprise egg on level 1 with a key 4. From this root egg, let's place 2 nodes below, so we need 2 surprise capsules to store the pointers, one for each child that is connected with a parent. On the left, the node with a key smaller than 4, 2, and on the right, the node with a key bigger than 4, 5. Let's assume the left surprise egg on level 2 is also a parent and have children on level 3, with keys 1 and 3. For each connection between 2 nodes, called edges, pointers from the parent to each child must be added. Nodes at the end that don't have any children are called leaves. The tree's height is measured by the number of edges from a specific node, bottom to top, so the leaf node has a height of 0 and a root a height of 2. There are 2 approaches to traverse through a nonlinear tree structure: breadth first search, BFS, and DFS, depth first search. In BFS, all nodes on the same level are explored first, then the child nodes, starting from left to right first, then from top to bottom. The BFS traversal is 4, 2, 5, 1, 3. In DFS, all child nodes are explored first. There are 3 traversals. In pre-order traversal, all nodes passed are immediately checked, then move top to bottom. The pre-order traversal is 4, 2, 1, 3, 5. An in-order traversal is a check from left to right. The in-order traversal is 1, 2, 3, 4, 5. A post-order traversal is a bottom to top order from leaf to root. Check a node only after you check all of its children. The post-order traversal is 1, 3, 2, 5, 4. How do you execute operations like search, insert, or delete? The binary search tree is recursively built. One node has max 2 children that are binary trees themselves. When searching an element, on each level the number of elements are halved, which makes the complexity big O of log n. However, in an imbalanced tree, the search can take linear time in worst case. Inserting an element takes constant time due to a simple change in the pointers for the linked list. However, finding the fitting insertion spot in the tree takes additional search time, which makes the complexity similar to search complexity. Also for the deletion, deleting itself takes constant time, but changing the following connection for the remaining elements requires search time. That makes the complexity similar to search complexity too. The space complexity is big O of n. In summary, binary search trees are recommended when search speed or inserting and deleting of elements are important, for example, for executing autocomplete activities or spell checks. Next topic, graphs. A graph is also a nonlinear data structure and is similar to a tree. However, there are some differences. The nodes are called vertices, cycle connections are possible, and graphs don't have a root node. The graph shows how objects are connected to one another. Therefore, vertices, but also connecting edges, can store data. Let's assume these 5 surprise eggs represent a network of persons. The connection lines between the eggs could stand for the strengths of their network, for example, how often they have met. Red and blue egg 3 times, yellow and blue egg 9 times. In this example, the edges have no sense of direction, so the graph is undirected, but edges can have a direction, meaning the relationship between 2 nodes only applies one way and not the other way, for example, when navigating from A to B. One characteristic of graphs is connectivity. The more the elements are interconnected, the stronger the overall connectivity is. Only if there are no disconnected vertices or subgraphs, the overall graph is considered to be connected. There are several ways to represent connections in a graph. An adjacency list is one example. In an adjacency list, a graph is represented by a collection of lists, each storing the neighbors of a vertex in the graph. So in the case of the surprise eggs, the blue egg is adjacent to green, yellow, and red. Red is adjacent to blue, orange, and green, and so on. Running searches like DFS and BFS is the same like with trees. However, as there is no root in a graph, you can start with any node. For searching an element by traversing, every edge and vertex is checked at least once. This search complexity is often described as the number of edges plus the number of vertices. Adding a vertex or edge happens in constant time, while deleting a vertex requires worst case a change of all edges and vertices, and deleting an edge requires a change of all edges in worst case. The space complexity of graph structure requires memory space for all vertices and all edges. In summary, graphs are highly recommended when analyzing the relationship between objects are important, and adding or deleting new elements and connections is frequently required. For example, for representing social networks or recommending products based on individual consumer data.